So this is our monthly model risk, introduction to model risk event. We do that every month, and every month is like Christmas because we change the model every month. Now we have our energy series. The past month we did one model for a solar panel model, right? A solar panel energy estimation model. Today, as you can see in the picture, we're going to talk about wind farms. And the main idea here is that we're going to take one simple model that we design, right, with help with some experts that we had, and then after that we're going to add some distributions to it. That's the main idea of the model. So the model today is going to be a complete MPV model project evaluation for a wind farm. So you will see it's fun, and it has a lot of different distributions and important variables, and I hope you like it. Just in case, we're going to use something that it's called ModelRisk, and ModelRisk comes from a company called Vow Software. They are the the ones who programmed it, build it. Their home office is in Belgium, with more than 25 years of expertise doing this. They started as consultants, and then they became trainers in quantitative risk analysis, and now they evolved as the developers of software. And they have three main products: ModelRisk, which I think it's 19 years old right now, and Tamara, which does Monte Carlo simulation on top of P6 files, and Pelican, which does ERM, which is enterprise risk management. So at the end of the presentation, I will share with you a couple of links where you can see videos where we introduce Tamara and Pelican as well, in case you think that they are going to be a fit for your organization, right? Now about us, about the ferry field. Well, Jameson works with me at the ferry field. I'm not sure if Ruben's here or Aman, right? We are a partner of Vow Software, and we can of course be your partner in quantitative risk solutions, and we guide organization from tool selection to successful adoption of that tool, right? So we can help you through all the way, and we can help clients derive the maximum value from their software investment. That's the main idea. We do consulting. We're actually doing 2 or 3, hopefully, consultings this year. We're doing 2 right now, but the 3rd is in the works. The Fairfield Group, we have a global network of consultants. Right? I saw a couple of them with just connected, and thanks so much for coming and for your time. Ensuring tailored support for clients' worldwide needs. That's why, for example, if you have a real estate model that you want to build, so we will have a consultant that's going to do that. And or if you need an oil and gas model, or if you need a construction model, and depends, of course, on the time zone or wherever you are, we can help you with that. That's the main idea of our consulting services. As I said, energy infrastructure, financial services, technology, manufacturing, right? It all depends. What is it that you do, and how is it that you need us, right? And some of our clients are there, right? Now, let's go to model risk. So model risk, and I'm going to show it to you here. Model risk, let me create a new file so I don't spoil you, right? So model risk is a Monte Carlo simulation add-in that sits on top of Excel. As you can see here, you have a very nice ribbon that is going to be on top of Excel. And what you can do, you can define inputs and outputs on top of your model. And that's exactly what we did, right? We had our model here. This was our energy model, right? This energy model did the calculation of energy, the revenue estimation, the potential energy losses, the costs, variable and fixed, the calculation of EBITDA and things like that, right? We had all of that already built in Excel. So what you can do with model risk, you go one by one, identify the variables. For example, the, I don't know, grid outage, right? Grid outage. So what's the percentage from the total energy that you produce with your wind farm that is going to be decreased because of the grid outages, because of curtailment, right? Because of electrical availability, etc., 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 right? And all these different variables, that's what we did. We created these variables here for each one of them. And what happens is that we replace these variables with distributions. That's what we did. So this could be per distribution. This could be normal distributions, triangular distributions, etc. And the main idea is that the moment that you run this process, you run this model, right? Run the simulation process on the model. What's going to happen is that you will fetch samples from each one of these distributions automatically. This is going to be random, right? It's not that you control where from the distribution you get it. It's totally random. And then the model is going to be recalculated thousands of times, this model here. So it's going to be recalculated thousands of times, right? And every time you will get a different result, because the results, instead of having a static variable A for example, grid average that perhaps the reference was 2%, now you have a distribution between 2 and 6%. So one time it could be 5, one time can be 4, one time can be 3, again it could be 5, etc. Right? So after you finish, you will get something like this. You will have a long table with the results for all the outputs of the model. And what you can do, you can generate statistical calculations on top of that, like for example, generating histograms or calculating tornado charts to see key drivers, calculating percentiles, the mean, the median, etc. Right? So what happens is that you added one additional layer to your decision-making process, which is the probability. Before, when you didn't have this, it was like this. For example, if you calculate the NPV, if the NPV, the single NPV calculation was positive, you do the project. If it's negative, you don't do it. But you don't know, you see the gray area, right? You don't know what happens if you move this variable up, this variable down. You don't know all the different ranges that you have there. And you don't have the upsides and the downsides. You just know, you just have one number. And that's not enough. And with Monte Carlo simulation, what you do, you can create this, you generate the histograms, the plot, as I was saying, right? And that's exactly what we're going to do. Now, as for the energy model, I will explain it from the Excel sheet, and then I will explain it in the presentation. The energy model is very simple. It has these 3 inputs here, 3 sheets. So you have the inputs, the model itself, and the projection. Right? The inputs, I did it very, very simple, right? The inputs are for example, how many turbines you have, right? The big turbines, what's the rated power of each one of them, and total installed capacity, 400. Basically, you multiply this times that. Hours per year, 8,000, almost 9,000, right? Then we have the capacity factor of 42%. So 42% represents a long-term net capacity factor, right, with a strong wind resource, etc. So what I did, I generated all this knowledge here so you understand what it is, what you're doing. Because otherwise, what's happening is that I'm not an expert in energy, right? What we do is we basically orchestrate, we learn about the topic, but we add this additional, as I was saying, this additional uncertainty layer on top of that, right? So what you should do, and this is a recommendation for your models, is that you should add this knowledge there so you remember why is it that you make this decision, right? Otherwise, it's very difficult for you to remember, right? Then you have, for example, all the energy loss factors which you have here, right? We're going to call the energy loss factors, maybe, I wouldn't say green because this is energy loss. So let's go there, right? The energy loss section. And remember that this is a simple Excel model. So you can change that and you say energy loss factors like this. And this is any Excel model. So please don't think, because sometimes people come to us and say, well, you have special format for ModelRisk. No, it's not. So you have energy loss factors, you have a potential discrete event. So we set up one discrete event, right? And here you have the financial inputs. Like, for example, you will invest $450 million in this. That's the price that you're going to sell this to where it gets to the grid. We don't have any share with a merchant, right? Otherwise, the model is prepared for that. Then you have the variable cost, 22. That means that, imagine you sell it at 25, you have 22 variable cost, and then you have a fixed O&M per year that's going to be 5 million, which is more or less 1% of it, a little bit, right? So what we're going to do, right? We're going to generate a projection for 20 years, right? With some energy annual degradation, right? with a price escalation of 2%. You see, all of these normally are in the contract, right? You have a price escalation, O&M escalation, and then you have a discount rate for this, which was 8%. That means that maybe you're going to develop this in a developed country. I live in Ecuador in South America. Maybe the discount rate most likely is going to be higher, right? Because our risk is a little bit higher, right? Now, you have the inputs here. You see, the inputs, they describe the capacity, they describe the energy losses, the potential discrete event, and the financial inputs, plus all the factors that are going to affect the 20-year projection that we have there. Now, this is one. The second thing is the model, and the model is very simple. The model was, again, the inputs 400, and then what I did, I generated, let me see, these colors doesn't help much. Let me change, let me see very quickly, right, the color, right, to make it, here you go. So this one here, it's how the net gross energy is calculated, that it starts with the gross energy, and then you go step by step as you have these energy factors. I'm going to touch on that. Finally, we have the projection for 20 years, right? So start here, you have this net energy. So everything starts with the net energy, and then you have the pricing that you're going to get to sell it for, the revenue, the variable and fixed income, the EBITDA, the free cash flow, et cetera, until you get a potential NPV, as I was saying before, right? If I don't run any simulation here, if I disable the simulation, you see your NPV is going to be 95 million, and your IRR is going to be 10%, right? Discounted at 8. So it seems like it's a good project. So that's what we're going to do. At the end, I'm going to run what I call some scenarios, and these scenarios are going to do some what if calculations, right? Now that I explained the model, where are things? So now you have an idea of how difficult was the model to build. Imagine it was three sheets, and this is the description that I just did about the model, right? So the model utilized, remember, has 50 turbines, each megawatt per each one of them, so it's 400, right? Now, the annual energy that you will have is 400, right? Imagine that you have this 400 megawatts, right, per turbine, times 8,000 hours, plus 42% capacity is 1.47 terawatts a year. What does it mean? It's in US standard, it's going to provide energy for a city of 100,000 people. In Europe standards, it's going to be 41,000 people. And Latin American standards, which of course we have less infrastructure, it was like 400,000 people. It's like the city where I am, right? And the approximate cost is 450 million. That's what you have, right? Now, remember that what I said. What are the main variables of the model? One is the capacity, right? And the capacity is between 35 and 48%. So I'm going to start giving you ranges, right? And these ranges are the key for the model, because these ranges are going to be converted into distributions. That's the thing. If you don't convert these ranges into distribution, you're going to have a discrete, a deterministic model, one scenario only. In this case, you have a range. This range represents, for example, a long-term net capacity factor for a modern utility scale wind farm with strong wind resource and typical losses already handled separately. That's one. And you can always change it. Again, maybe you say, oh, but I always do mine with 65. That's perfectly fine. You go there, but also change the distribution that you're going to use. Remember, this is for introductory level. So if you already know how to do that, please, maybe you can focus on the model yourself, right? But you know that. Then you have energy losses. The energy losses is a series of factors that affect and attenuate the amount of energy delivered, right? It's not that you have the turbine and the I don't know, you have, remember, 8 megawatts per turbine. That doesn't mean that each one is going to produce 8 megawatts at the end. No, you have what we call an energy losses, which is something like this. So I'm very sorry if you have some syntax error here. I tried that many times, and my friend LLM gave me something very decent. I wouldn't say that was perfect, but it was very decent. Here you go. You have a electorial availability. It would be electrical availability. These factors are, for example, maintenance losses for scheduled maintenance, electrical availability, right? You have your In this case, your wind farm is connected right to the grid, but maybe you have scheduled and electrical availability. It's not like these things, they run forever without maintenance. So you will have perhaps around 4% of that curtailment and grid constraints. I'm going to see that 7% mechanical losses, 3 environmental, 2 grid losses, 2 major failure losses, let's say 2% because of some accidents, very heavy winds, etc., inclement weather, right? So perhaps you will have around 80% of delivered energy from the 100% potential energy, right? And here we have an explanation of each one of them. So what I did, I added the range of each one of them, right? The electrical availability, for example, availability balance of plant, typical collection system plus substation with switching. You see switching that you have to do transformer issues and things like that. Curtailment. I'm sorry. John said if we can have the Excel file afterwards. Of course, you can write to me. Here's my email, because I already did this once. Let me send my email here. I mean, maybe you can send the email right now. And I sent it to everybody, and everybody was very upset because they said I didn't want the model. So if you can write to me and you ask for it, like John, you did, that would be perfect. More than happy to share with you the slides and the model, right? We're more than happy to do that. You will have curtailment between 2% and 12%, typical grid congestion, dispatching structure, market constraints, right? Sometimes you just have an overflow, you just have to wait. Mechanical availability, right? Typical electrical balance of plant, like occasional switching, etc., right? Like this. Then you have environmental stops. You see that sometimes you have to wait because of wildlife traffic, so you have to wait for the verse to move. You cannot do that. Noise compliance, shutdown windows, operational constraints, right? During sensitive periods, for example, bird migration. That's something that I was talking to a friend that knows about this, and he was telling me that sometimes they have to stop, and that I think it's great. The grid outage, you see, small but very realistic energy loss from transmission and a major failure. So what I'm going to do, I'm going to move to the model and show you how to do this. So I'm going here to the inputs. For example, here you have the mechanical availability. You see, it says it's 96%. But what I can do here, because this mechanical availability, and we're going to use only this variable to do this this example. You see that you can see where are the dependent variables, and you can go there to the mechanical availability, which is here. You see, you multiply the gross energy after the mechanical availability, which is inputs B9, and B9 is 96%. So what you can do is you can generate, for example, here and say, well, mechanical availability could be between 1 minus, right? Because it's going to be in almost 100. It's, let's say, 1.5%, 3%, and 4.5%, let's say, right? So these are the parameters of my distribution. I did it symmetrical to make it simple. And what you can do, you can go to ModelRisk here, say select distribution, then you will have a palette here with more than 100 distributions, right? So this is the ModelRisk. The good thing is that this is for very basic amateur users, let's say, and very advanced and complex users that want to really dive deeper into the distribution. For example, I would say, let's use a PER distribution. So the PER distribution, the good thing about that, and I'm using it in all the variables here, is that it has 3 variables: the minimum, the most likely, or the mode, and the maximum. So if you click on this little arrow, you can say this is 1.5. You click on OK. See, link cells for the mode and link cells for the maximum, like this. And this is the PER distribution. That means that when I run the simulation, this is going to fetch samples from here, 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 etc., right? And you know that it's going to be between 1.5 and 4.5. Remember, so you already selected the absolute limits of it, which is something that we needed, right? We needed to have the absolute limits of it. So you insert to the worksheet, and then you see you will have what we call a Vos PER distribution, C9, D9, E9, right? Like this. If I turn on the simulation, take a look what happens. you will have that. But you see that the 96 doesn't change. So what I have to do, right, what I will have to do is, first of all, right, as you see here, right, I will do this equals 1, right, like this, equals 1 minus this. And take a look at what happens. Now you have this changing, meaning that if you go to the model, this one here, mechanical availability, which was not changing before, right, this one in yellow, now it's going to change. You see? Now it changes. And this changes as well. That's why I had this graphic here. So you can see how it oscillates, right? And that was the main idea. Then I come back here. And one thing that you always have to do in when you use model risk, and that's a best practice, is that you can set up the cells are input or output. This is going to be an input. So you come here and say, well, this is an input. This is we calling mechanical availability list. And then you click in OK, like that, right? So now I have all the inputs. If you want to add colors to these inputs, you just have to go here to the model, right? You filter and say, give me all the inputs, like this. And you can say, I want this, all of this in orange, for example, right? And all of them are going to be orange. So you don't need to, go cell by cell and recognize it. You just go like that, right? Now, for each one of the different energy loss factors that I mentioned, you see here that you have mechanical availability, which is the one that we just created, right? Electrical availability, you already have that as a per distribution. The wake loss, again, was another per distribution. This, the curtailment, like this. And of course, I can do that with that, right? I can definitely do this with all the cells, right? That would be great to do. Now, what you can do after you do that, then you can have what we call a major failure probability. What does it mean? That you have here a 25% probability of having a major failure probability. The major failure probability is going to be 20 days. I'm going to leave it like that. Of course, you can add, and that's the nice possibility of this, you can add any number of distributions at any time. So if you don't know the number of days, you can say this will be between 15 and 40 days. Otherwise, you can say, as I did, this is going to be exactly 20 days, right? But you can change that at any time. For the probability, we will do what we call a Bernoulli distribution. You see here that every time that we simulate, right? Sometimes it's a 1, 25% it's a 1. So that means that every 4 times that I press F9, which I'm pressing right now, this is going to become a 1. If it becomes a 1, what's going to happen like this is that you're going to have an impact, an energy impact event base, right? That's going to be equal to the 20 days, which is V18 divided by 365. That's a factor in the year multiplied by C17, and C17 is this. Right? So that's going to be 5% of the year you're going to be down. So basically that's the equivalent of, let's say, let me do it again, right? All the, in this case, see here, V18 divided by, this is equivalent to the expected 1% of it, right? Maybe this is going to be better if we put it in percentages like this, right? Like that. And sometimes it happens, sometimes it doesn't, right? That's the idea. If you go to the model here, you see that if you have a major failure, if you don't have the failure, the same energy that you have here, the 947,925 is going to be still, is not going to change. But if you have a failure, you see, it's going to change. So if this number is not equal to this number, that means that you had a failure like this, right? So let me go back. So once you have this, you calculated the net energy, which is the very, very important number. And that's what I was saying here, right? See here, the main variable of the model was the capacity factor applied to the net energy. So if you come back to the model, this number here, the 193, is going to be the first one here. You see the 1,000,093 is going to be the one that you have here. Now, what happens next, right? Now you have the net capacity factor, you have the total loss, etc. So what happens, because that's normally the question, right? What happens if my distributions are wrong, right? So why is it that these distributions are so important? One, because they define the shape of the risk, not only the mean or the average. They define the shape. They tell us how wide the outcomes can vary, how fat the downside is, how likely P90 shortfalls are, etc. So without the distribution, the model, remember, is deterministic, but with the distribution, the model becomes very, very simple to use in decision making. Now, what happens if the distributions are wrong? For example, if the variability is underestimated, and normally this is what happens, right? That several studies show that we normally underestimate risk. The P90 looks too optimistic. Our depth sizing becomes aggressive because we think that we're going to be much better, and the tail risk is hidden. So that gives us some false sense of security. So we have to be very careful with that. What happens if you have a super conservative person there and the variability is overestimated? And all the time you're thinking about the worst scenario, the perfect storm, right? So the project is going to appear too risky. For example, instead of saying between 2 and 10% of curtailment, somebody will say, no, it's 15 to 50. So that means that you're going to live on a constant crisis. Your capital cost is going to increase, right? Because you have a lot of variability. And maybe some investments or the investment is going to be rejected unnecessarily. So you created value destruction, basically, from excessive conservatism. So you have to be very careful with this, right? This is the analyst risk, right? The A and B. If the shape is wrong, let's say that you have, okay, you have the boundaries are okay, but the shape is wrong. For example, instead of choosing the normal distribution, you change the pair distribution, or you choose a triangular or Weibull distribution. Sometimes you underestimate extreme downside, you overestimate the upside, you miss clustering events, you misrepresent tail exposure, etc. So if you have the shape wrong, that means that most likely this is not going to be good for the model. So you have to be very careful with that. Why is that? Because the tail, you remember, the tail is going to do the P90 of the energy, the bankability of the project, the financial resilience, etc. Normally these distributions go like this, and our P90 or P80 is going to be here, right? So it's very important that we know what's going to be the effect of that, right? Bottom line, the distribution is not a technical detail, right? Let's not do it just because. Let's benchmark, read, go to the academia, go to reports and things like that. Use the deep research of the LLMs. Try really alternative sources, right? Because if the distribution is wrong, the simulation is going to be precise, but it's going to be misleading. And the thing here is that you don't know. Because as I just did, I created a pair distribution as an example for you guys, but maybe this is not what I need. This was a triangular distribution what I needed, and that's the main issue with this. So you have to be very careful with that, right? Now, for the financial model, we start here, right? So we have here with the inputs the model. For the financial model, which is here, the net energy is the starting point. As I said before, the net energy comes here after all the energy losses, after the capacity, after bird migration, etc., right? And it's used to calculate the revenue. So you will multiply, remember the blended price. In this case, we don't have a merchant, so the merchant share is going to be 0. But should we have it, of course, it's going to be included in here, right? And then you just multiply the two. After that, you multiply the $22 that we have before as the cost, right, times the energy as well. So that's why you have this. And a fixed O&M of 5 million, which was, remember, this is the first year. So the total O&M, fixed and variable, is going to be 29 million. Then the EBITDA, very simply put, is going to be 52 million. Of course, you have much more to do with that. But the main idea is that you have a baseline model that you can improve. Now, what we would like is hopefully for you to use this model to make it yours and hopefully to show it to us and say, well, I did this and I did that because it worked, right? Now, what else you have? You have your capex minus 450 million. Again, we simplify it here. You see, it's this big investment here. Perhaps it's going to be done during the first 3 years or 4 years, or maybe we have to put the repayment of debt in a different financial model, etc. You have the cash flow here, right, like this. Then we have the discount factor. Remember that we had a discount rate of 8%. Then we have our present value of the free cash flow, which is this, and then we have the cumulative. So of course, as you can see, as we have such a big difference between the price that we're going to sell the energy for and our costs, it seems to be it seems to be positive. What if the cost, instead of 22, where was it here? It's 35. If the cost is 35, take a look to the model. You're going to lose money, right? Minus 100 million, and the IRR is only 4%, just because I changed this, right? And this is what we're going to do in the scenarios. We're going to change the cost just to see how fragile or robust the model is to support the scenarios, right? Like that. So what we do, I just explained this, right? The variable and fixed costs. We have the total O&M, that it's the sum of both. Then we have the EBITDA, which is the revenue, minus the total O&M, right? Like this. And we have this financial model there, right? After you do that, of course, you can calculate. I think that we had this potential payback calculation. Simple payback was like 11 years or 8 years, depending. This was taken after we run a simulation, right? You have that, you see, potential payback, 8, 11, 9 years. This is going to move depending on the variability. Your NPV is going to be 100 million, which you have here. See here, but you see, this changes. So which scenario, and sometimes you have this question, right? Which scenario should I choose? This one, this one, this one, and this is wrong, right? And this is something that I wanted to clarify, because from the last model that we showed, I had a couple of emails asking for that. So you were doing F9s, right? So which scenario should we choose? The one that you choose is the scenario after you run the simulation. That's what we're going to do now, right? So I go here to model risk, and I will go to the settings just to validate. You see that you have, I will do one simulation only. It's going to be called the baseline model, the base model, right? And what I will do, I will run 1,000 iterations, meaning that I will press F9 1,000 times automatically. And this is going to integrate here in the outputs and inputs. You'll see here, every cell that was an output, like for example, the NPV and the IRR, right? It's running now, right? It was very quick. Let me do it again. So you see what happens. You have this, you see? And now you have this. So you will see a bar doing that. Then I can go to the results here. See, they're coming here. Here you go. So you have the base model. And the base model is going to look like this, right? This is my NPV, for example. My NPV is going to be a histogram of 1,000 samples, right? 1,000 samples. And what this is saying is that with this configuration of the model, the probability, right, of the NPV for being negative is 7%, right? This corresponds to all of that. The probability for the NPV being positive is all of this. That's 93%, right? That's what we need to know about the NPV, right? Because if I say the NPV mean, for example, here, is going to be 86 million, that's okay. But what I need to know is what's the probability of being negative, which is going to be this corner, the left tail, right? Remember that we were mentioned there, the tails. That's one. But if I want to do, I can take a look and say, well, what's the IRR? The IRR is going to look like this. Remember, this is something very important here, that I should come, let's say, to another histogram. Let me do insert histogram, right? And I will go to the IRR. Why is that? Because now I have the measures of the IRR here. Same thing. Is this going to be more than my, I don't know, discount rate or not? Or is it going to be more than 0, right? It all depends how you like to measure all these financial outcomes, right? So now we have one, which was the NPV that was here. There was at least 7%. So that means that you have 93%. It was a very positive project, 93% probability of making money, right? To make it work fine. Now, what you can do what I call the tornado charts. And the tornado charts, what I'm doing, I'm showing a tornado chart on the NPV, which shows the contribution to the spread, meaning this is the risk explained. So 97% of the risk is explained by the capacity factor. You see how important this variable is. Remember that slide that I said, what are the most important variables in the model? The capacity factor, right? Because you had a very wide distribution too as well, right? You have the capacity factor here between 30 and 45%. But let's say that the capacity goes to from, I don't know, 40, 42, and 45. You see, it's less variable. Remember, perhaps it was too wide, it was too conservative, and it was very, very pessimistic because it was the capacity factor of 30. So I change the distribution, I run the model again. And that's the mechanics of how you use Monte Carlo simulation. You change the parameters of the distribution, and then you run the model again. Right? So we'll go to the results here, and you'll see that everything changed most likely. You see, now the capacity doesn't have such a big variability. Remember, it was 97% before. Now you have 85%, and the electrical availability is the one that you should worry about, as well as the mechanical availability. You see? So it's just a matter of knowing the ranges. What if we go to extreme here, go to 41, 42, and 42.5%? Very, very small. So we have a capacity that is, I don't know, very, very thin in terms of availability, in terms of the width of the distribution. So if I run it, you will take a look to what happens, right? I run the simulation, come to the results, you see, and now you have the electrical ability to the other side. And you see, and the capacity factor is only 29% of the risk. And now the electrical availability, which is fine, goes to the left, right? That's what it's moving the model, because the capacity factor is not as wide, is not as effective right now, right? Why? Because it has a very small range. So the wider the range, the bigger the risk. So maybe I will leave it here in, I don't know, 40, 42, and 45. Here you go, right? And then I will run a new simulation. You see how it works. You just change the distribution configuration, and then you just run the model again. That is why we had this slide that said, what if the distributions are wrong? Because we have to be very careful with that. You see, it's very simple to mess up with the distributions because the model is going to work anyways, right? The model is going to look good anyways, right? And we have to be careful with that. So we have the tornado chart. Now that we have a projection, and that is not in the presentation, remember that we have this projection, right? So what I can do, I can come here to the free cash flow, for example, take a look at this, right? Select all of this together, like this. I wouldn't select the 450 million because it's always the same, like this, and then I can go and say, generate this as output. The range name is going to be free cash flow, and the names for each one of them is going to be the cash flow number, like this, the last name, let's say, of each one of them. So this is going to generate an additional set of outputs like this. I can run the simulation, right? And this is something that you will have to look in the video so you remember. I'm running the simulation, and you will get another graphic, which is called the trend graphic, like this. Right? So you insert one graphic, so you go to insert trend, and then you will see the trend graphic of my cash flows, like this. Of course, this is very positive. Why is that? Because my cost is very small. Right? Now, we know that we're going to do the project, we have $22, etc. But what happens if I create a scenario like this, right, where I have 5 different scenarios, where I have 22, 25, 28, 31, and 35 as the cost, because I want to do some sensitivity analysis. Why? Because maybe I will have a partner, maybe I will have somebody that's going to share it with me, or perhaps the government is going to change the tariffs, or perhaps some new regulation comes, etc. So my costs are going to be higher. So I want to know where is it that my costs are going to be, in the limit. Remember that with 22, we have maybe, I don't know, 9-10% probability of being negative. Let's see what happens here. For this, I'm using something that it's called sim tables. We have a video about that. So if you're interested, of course, I will show you where the videos are. So it's called sim tables. And what I will do, I'm going to run 5 simulations on one. That means that I'm going to change, you see here, number of simulations 5, and the simulation name, now it's going to be this, right? Like this, 1, 2, 3, 4, and 5, meaning that this value here, 22, 25, 28, 35, 31, and 35, are going to be mapped to the cost. What I'm going to do is do both sim table to this, right? So first time it runs the simulation, it will run 22. Second time is going to be 25, 28, 20, 31, and 35. So I'm going to start. You will see that it's going to take a little bit longer because I have 5 simulations. But the good thing is that you didn't have to do this by hand, right? And this is what the sim table is going to help you with. Not doing this by hand. Imagine you will have to run a simulation with 35, then 31, then 28, then 25, then 22. You see, now you have simulations 3 or 5, 4 or 5, etc. So it automates, now that we have this era of automation, so we have this forever, right? Automation of running scenarios. So you see what happens. If you have 22, now you have 0% probability of being negative. If you have 25, 0%, 28, 0.9%, 31, you have 20%, and with 35, you have 94% probability of being negative, the NPV. So you know that 34, 31 here, this is the limit, right? Your costs cannot get higher than $31. Otherwise, you're going to have an issue with the NPV. The project is not going to be feasible. Why is that these numbers change? Remember, because I changed in the model the range. If I make the same range as before, 30 here, you see, I can just do a what if, I run it. This is going to run the 5 scenarios again. And when it runs the 5 scenarios again, this is going to come and sorry, this is going to come and modify the probabilities. So you will see now it's in the 4th simulation. It's finishing. Let's go to the 5th one, right? And you will see that we came back to the numbers we had before. Remember, 7%, 20%, 34, 64, etc. So if I come back to the ranges where we had the capacity before, this is not the number, right? Perhaps, let me do it here. Perhaps this is the number, right? 25. Like this. So those are the types of things that we need to take care of, right? As you see, the logic of the model, I imagine that the majority of you already have. Then you have to add this layer of probabilities, right, of ranges in this way of distributions. Like I did here, I did only 3 or 4, right? 5, because I had one that we did today, right? Plus the major failure, right? But you see how simple it is. So my recommendations is you always have this portion. Don't hard code the distribution here. Put the distribution parameters there so you can see them, so you can play with the distribution parameters. That's the message of today, right? You see, plus you have, of course, you have a very nice model and projection, plus you have the scenarios. And the good thing is that we always had a question that was very, very simple to answer. What is the probability of the NPV being 0? That's the, in this case, the decision-making criteria. If you have also a payback, if you have also, I don't know, that you will never have a cash flow that it's less than, I don't know, 100 million, etc. You will have more different criteria that you will have to meet, but this is the type of things that you will have to do. So that's my recommendation. Always take a lot of care about the distribution parameters. You can run it. We can add correlations. We added correlations in the previous model. So remember, you can just say, I'm not going to add them, but if you want to add correlations, you just select that. Go here to correlation, multivariate copula. You click on continue, and you can add the correlation matrix here, right? It's going to be very simple. Right. So this is what I had for today. I'm not sure if you have questions. I know that Yana asked me for the model, John as well. I'm not sure, Igor as well. So more than happy to share with you. We will publish this as a video in our YouTube channel that I am about to show in a minute. So this is our YouTube channel. So you go to YouTube, Fairfield Group. Let's see here. We have more than almost 200 followers. So if you want, please subscribe, because we're reaching 50 videos with today's and tomorrow's webinar. We're going to reach 50 videos, which we are very proud of, right? And we have different playlists as well, right? This is going to be, for example, in the energy playlist, we have one, now we're going to have two, right? And we have our past, for example, our Quantitative Risk Summit second edition, the Quantitative Risk Summit, the first edition. We're going to have a third edition in March. And what I will send you is this virtual sessions page where we have all of our events. For example, this event here is for today. Tomorrow, if you're interested on automated things with ModelRisk, please make sure to register, of course, for free.